when you look at petroleum geology, it's a course that is structured in a sequential order. What do I mean by sequential? When you look at it, it's chronological. It starts with the origin, migration, accumulation, then production. The origin, migration, accumulation, and then the production. So when you look at your course, curriculum, the production is not there. Generally, it's not there, but it's a thing that I have plotted for a very long time now, that should be part of the curriculum. But since that has not been affected, and knowing full well the importance, I have taken it upon myself to be teaching it, pending the time the thing will be officially added, because it is definitely going to be of great advantage to as many of you who want to practice in the oil industry. So today, as I said, it's going to be a sum total of what you have been taught, and more or less a summary. Now, talking about the origin of petroleum, you cannot talk about the origin of petroleum in isolation. You have to hinge it on the transportation of sediments and then the deposition of same. There are two schools of thought as per the origin of petroleum. A school believes in abiogenic, that is a chemical reaction mode of origin. But another school believes is biogenic. And the first group, which is the first school of thought, that has since been discarded, the abiogenic origin. The reason being that a lot of evidences have shown that petroleum actually originates from biogenic means. So, what is the principal contributor? Please mute your this. Who is that? Who is that person? Who is T? Who is T? Who is this T? Now wow. So as I was saying, there are a lot of evidences to that effect that petroleum actually generated from biogenic means. From the slide I've sent to you, you would have seen some of those evidences. But one prominent one is the presence of cellulose. By the time you carry out detailed study of a crude oil, you are going to see the remains of all those cellulose, because they are quite resistant to further biodegradation. So they will still remain within, you still see their traces within the crude itself. So, and some other evidences which have shown that indeed they are biogenic. So it's not ambiguous at all. And it's not a thing that is more controversial again. So petroleum originates from organic remains, plants and animal. In the slide you have, I don't know if some of you have taken time to look at it, listed are various food groups that you have that serve as a precursor to the origin of petroleum. Example there is your protein, you have carbohydrate, you have the lignin. These are materials that come up together. So the organism, by the time the organism would have died, they are buried. Their mode of burial must be very rapid within the sediments. From your dimensional scales for sedimentary particles, we have particles that are within the range of greater than 2 mm. You have the ones that are between 0.063 micrometers and 2 mm. Then we have the ones that are below 0.63 micrometers. The ones below 0.063 micrometers consist of the silt and the clay, whereas the one that range between 0.063 and then 2 mm, that is where you have your sand particles, and then greater than that is where you have your the gravels. Now, when you have these materials being transported, I mean the particles, they are transported with the organic remains, and as they are being transported and deposited, those organic remains will not be found in a very substantial amount within the quartz grain, meaning that from 0.063 micrometers and above, you are not likely going to have it. And the simple reason for that is because of the surface area. The surface area is so thin as to cling onto those materials. So in the process of being transported, they are winnowed out of the quartz materials. So you now found out that it is within the particles of less than 0.063 micrometers that you have the organic remains, which is essentially the silt. And from the dimensional scale I mentioned earlier, that is the gravels, the sand, and then the silt and the clay, you know that when they get solidified, that your granules, I mean the gravel will either give you a conglomerate or you have breccia. The sand will give you sandstone, and then the silt clay will give you more stone, which will later transform to what you call the shape, which is the source rock. So it is that source rock, the so-called source rock shape, that you have your organic materials remaining. So by bacterial activities, you now have that organic material transformed into what you call kerogen. So it is really the kerogen now that is the precursor to hydrocarbon that we have. But you know, those organic materials that you have there, they are in 3 types. Of course, there are 4 types. I've listed it there. You have the type 1, you have the type 2, you have the type 3, you have the type 4. The types is a function of the materials, as mentioned earlier. The proteins, the lignin, the carbohydrates, and the other food materials, organic materials that will constitute those precursors. You know, so but type 1, type 2 kerogen are essentially the ones that will give rise to what's it called? Crude oil. You know, talking of hydrocarbon, there are 3 fluids making up what you call within your reservoir rock. The first one is the oil, the second one is the gas, and then the other one is water. So hydrocarbon essentially deals with water, this with oil, and then and gas. So, but we are not interested in water, so we don't really talk about water, although it's one of the fluids that you have within the reservoir rock. So now that formation of your hydrocarbon is in stages, and the stages are equally 3. We have stage 1, we have stage 2, we have stage 3. The first stage is called the diagenesis. The second stage is called the catagenesis. The third stage is called the metagenesis. These stages, they are function of temperature and they are function of depth. They are function of temperature and function of depth. At the diagenetic stage, no hydrocarbon that is formed. Of course, there is, but not essentially the ones that are of economic value. You have the wet gas at that stage. It is that stage is just between 0 and 60 degrees Celsius scale that you have the stage that you have as your your metagenesis. It's just a scene where you just have just brief transformation of the organic materials. So the catagenesis is really where you have the transformation of your organic materials. That is where you have the generation of oil and you have the generation of gas. So, and it is at that stage you have what is called the oil kitchen. That is the cooking of all those materials, and then you have the oil window. I want to implore you that you get yourself acquainted with some of the things I've sent to you. In fact, most of what I've sent to you, you see, we have what we call the Van Crevlin diagram that detail those stages that I've mentioned. So please make sure you get yourself acquainted to that. So that after that, catagenesis is the metagenesis. At that point, you have the catagenesis ranging between the temperature of 60 degrees Celsius up to 110, 120. In fact, some literature will put it 130 degrees Celsius. So that is the window, I mean, what constitutes the oil window, the oil kitchen. But beyond that, yes, Chema, what's the problem? I've admitted everybody now, I guess. All right. So, as I was saying, beyond that temperature of 130 degrees Celsius, you discover that the organisms responsible for the transformation because of high temperature will be destroyed. So you don't have further transformation there. That stage is referred to as metamorphic stage. And what you have essentially there is dry gas, and you have coke, which is your graphite. So you don't have beyond that. That is just the stages through which you have your transformation of or generation of your crude oil or hydrocarbon. Sorry, your hydrocarbon. So that is that. Now, the source rock is not every shale that you refer to as source rock. There are some that they are not having enough organic material. There are some that have generated and they are no more generating. There are some that are still generating. So, but how do you know that? There is what you call source rock evaluation. The source rock evaluation are the methods in which you carry out to determine the hydrocarbon potential of your hydrocarbon, of your source rock. Is that understood? So there are different methods that can be used. You have what we call the pyrolysis. You have what you the vitrinite reflectance study. In fact, and we have the hydrogen index analysis. These are basic ones that are being used. Deliberately, I decided not to go into those details because it goes beyond what we can just be talking about online. And because of the peculiarity of this season, for a very long time, I've always been doing that. But I just decided not to bore you people with that aspect. But just to mention to you, that's why I said that. So for you now to just not every rock, every shale that you see that you just call so we say potential. Generally, that is for you to place it. You say potential source. So for you now to really say it's a source, you would have carried out all those evaluation, which is done in the laboratory. But or maybe some of you people may be working on organic geochemistry as your project. Definitely, you may need that one, and whoever that's supervising you will surely put you through, because it's not a thing, as I said, that can be talking about enough online. So we now believe that hydrocarbon has been generated by those processes that I've mentioned. So after must have been generated, the hydrocarbon formed will never reside permanently within the source rock. So the hydrocarbon generated will definitely want to leave the source rock.
So the means by which you have the hydrocarbon formed leaving the source rock to the reservoir rock is called the primary migration. That's the movement of your hydrocarbon or petroleum from the source rock to the reservoir rock is referred to as primary migration. Now, before I talk about secondary migration, let me briefly talk about reservoir rock. Reservoir rock, as Dr. Padala might have mentioned to you, they are the rock that have the tendency of accumulating, and they have the tendency or capacity of discharging their content. Reservoir rock, they are rocks that have that capacity or ability of reserving fluids, and they equally have the capability of discharging their content when when those things are being needed. That is simple definition of reservoir rock. Then, if that is the definition of reservoir, you now discover that reservoir rock must have some special features. And what are those special features? They are called the poropam. You call them, or may I say, the Petrophysica Attributes, which we sum up as poropam. Those petrophysical attributes are referred to, they are the permeability, then the porosity. Of course, porosity comes before the permeability. What is porosity? That is the total number of void spaces you have within your rock body compared to the total volume of rock. That's what makes your porosity. So the porosity can be connected, it may not be connected. So if it is connected, you refer to it as effective. If it's not connected, you refer to it as non-effective. But the connectivity of your pore spaces is what will determine if your rock will be a good reservoir or not. Because the connectivity now we describe the ease of passage of whatever fluid that is there, which is what we refer to as your permeability. So the more connected your pore spaces are, the better the reservoir rock will be. Otherwise, it will just hold on, just as I said, what the reservoir rock must be able to release. So if it's only holding and not releasing, then it's going to be a very poor reservoir rock. So having said that, you now discover again that it's not all rock that seem to be called reservoir rock actually a reservoir rock. From your sedimentology, you discover that we talked about, let's say, we look at sandstone as an example of a reservoir rock. Of course, we have limestone as well, but in this part of the world, especially in our area here, we have essentially sandstone as the principal reservoir rock. Now, when your sediments are transported, the longer the transportation history, the better, because that determines the maturity of the sediments. So if your sediments have not traveled far, the chances of you having admixture of particles is very high. And when you have admixture, definitely the reservoir quality will be very poor. Reservoir must be devoid of fine particles. Fine particles like clay materials. Clay materials like the ones that swell with introduction of water. Example of such is called the mortmarilonite. Mortmarilonite is a very troublesome clay material, such that if you have it within your reservoir, in fact, your reservoir is as good as being a non-reservoir, because the very moment water comes in contact with it, it swells. And the implication of that swelling is that it plugs the throat of the pores. So the fluid will not be able to move through. So that is why your reservoir quality must be very high if it's going to serve as a very good reservoir rock. So now Looking at the classic sedimentary we mentioned earlier, there are three types which are based on three things. One, we have the rock fragment content. Two, the feldspar content. Three, the quartz content. Now, if the ratio of your quartz is in excess of about 90% of the total framework, you are going to have a sandstone type called the arenite, quartz arenite. This type of sandstone is the best because fine particles would have been winnowed out. As a matter of fact, the grains are described as being grain supported. They are not mud supported. Because they are lacking mud, that makes them to be a very good reservoir rock. The other one, which is the content of your feldspar, that one is when you have feldspar content to be in excess of 25% of the total framework. In this situation, the type of sandstone you have is called the acoustic. It's not going to be as pure as that of quartz arenite. So it's another type of quartz, reservoir rock that is not as pure as the quartz arenite. In that case, even if it is having a reservoir, it's having a hydrocarbon content, for you to be able to mine it, it may require extra work to be done, meaning that you may have to enhance. That is by artificial means. So that is that. We'll talk about enhancement later. So the last one there is the lithic, where that's where we have the gray waki. They are very poor. The terms of maturity, very destructive, very, very poor. So you don't have you are not going to have a good reservoir there. So when the hydrocarbon now migrates from the source rock to the reservoir rock, it gets there in droplets. So by the time it gets there in droplets, you now see those droplets coming together. You have what we call the buoyancy. The buoyancy has to do with the relative density of those materials, fluids within the rock body. Now, I said earlier that there are three fluids making up you will find in your reservoir rock. You have water, you have oil, you have gas. In the order of their density, water is the densest. Hence, you are going to have water at the base. Right? Now, the next one to it is your oil. So oil ordinarily would be on top of water. And the least of density there is gas. This is going to be at the top of the three. So that is the order. So, but you now discover that this thing, as I said, they get there in droplets. So gradually you have the droplet now coming together. Before you know it, the droplet now becomes what you call the oil pool. Before you know it, the oil pool now becomes the oil feed. The oil feed now becomes the oil province. So that is the order. From droplets to the oil pool, from the oil pool to the oil field, from the oil field to the oil province. That is how it is. We have the Niger Delta area as an oil province, different oil fields that you find there. Then you have different pools of oil that is there. So that is it. But you see, when your oil or hydrocarbon gets to this reservoir, the movement within it is vertical. You always have vertical movement. That's the way it moves within the reservoir. So that movement will continue perpetually if there is not a stopper. So when there is a stopper, it annexes it. And that stopper is referred to as cap rock. If there is no cap rock, it continues internally. And before you know, it gets to the surface and seepages. So that is why for a good reservoir, one of the attributes is that there must be a cap rock. The cap rock now can be in form of structure. The cap rock now can be in form of stratigraphic content. Dr. Patola must have told you that. So, in terms of structure, you are talking about fold. You are talking about fold. You understand? And talking about fold, it's not all fold. The syncline now will not be a good habitat for your hydrocarbon, but rather you have the anticline. So, and if you are looking at it at all, as I mentioned earlier, you are going to search for your oil at the crest area. That is why you have your hydrocarbon at the crest area, and you only have the crest at the anticline. You won't find it at the syncline or synclinal part of your fold. So that is that. And then for your fault, definitely it's going to be a sealing fault. It's not going to be just any fault. If the fault is not sealing up, then there will still be migration. So it must be sealing. By the time it is sealed, so whatever gets there will just be annexed. So that is for the structural. Then for stratigraphic, we talk about your lenses. You understand all these pinch outs and the like. These are the ones that you form a reservoir rock. So all these turbidites, whatever the deep, what is it called now? Onshore or offshore, so to say, deep offshore. They are the ones that we harbor a very commercial quantity of hydrocarbon. So from the graphic view of what I've painted now, you would have seen that I've talked about the origin, the migration, then the accumulation. Origin of the hydrocarbon, that is from the organic material within the source. By them forming your hydrocarbon, which is a function of the kerosene.
So I can't hear you.
I said that be generated, it moves out of the source rock. Moving out of the source rock is what is called the primary migration. So it moves from there to this to the reservoir rock, and by it gets there in droplets. It's not like we flow like water. No, it's just droplet like that. So by the time it gets there in droplet form, the time will now come that the droplet will now coming together. But what determines the accumulation within the reservoir is a function of the sediment, that is the reservoir quality, which is a function of the transportation history and then the class of sandstone, the reservoir rock that we have in place. So I told you that when it gets to that reservoir rock, that the movement is always vertical, meaning that you can't have migration in the synclinal part of your fold, or rather it's the anticlinal part. So when you get to the, it's within the anticlinal that you search for your hydrocarbon. But there are 3 different fluids there. And then movement is a function of bias, which depends on the density of the fluids. Water is the first of the fluids, oil is the second, and gas is the third. Water is the densest, hence you find it at the base, followed by oil, then you find it on top of your water, and then the least there is your gas, which you find at the topmost of the 3. So that is how it is. And I told you that the movement will continue internally if there are no stopper. And what do I call a stopper? A stopper is what you refer to as your cap rock. So one of the attributes of a good reservoir is the presence of cap rock. Otherwise, you have the thing flowing to the surface in the form of seepages. And for some of you who might have maybe start hearing things about the Nigerian Tarzan, why you have within the Dahomey Basin, why you have tar sand in part of the basin and you have the crude oil, conventional crude oil and another part within the same basin is as a result of that. You know, when you go westward of the basin, that is towards Badagry area, you won't be seeing oil sand or tar sand, as the case may be there. You understand? But you've seen the conventional crude oil. That is why all this petroleum are mining there. But when you come to the eastward, that is towards the Niger Delta area, you are going to see that Okitipupa, Ogun State axis and the like. You are going to see there within that same basin, the same formation. You are going to see different hydrocarbon type, which is a very heavy one. So that is the reason why you have that kind of a thing. So if those structures are not in place to annex it, it comes to the surface, and before you know it, a light, what's it called? A light chain, a short chain hydrocarbon now be converted to long chain hydrocarbon, and thereby instead of being fluidy, it becomes very semi-molten. So you understand. So that is the reason. It is the bacteria or perhaps water washing. You remove the volatiles there. So that is that. And after you must your oil hydrocarbon must have been annexed. The next stage is to explore. You search for that.